Hey everybody, this is chapter 4. We're doing the whole thing. We got some math coming at you. It's probably going to be some review for you. Got some vocabulary that might be new. I've also got some fun history. Let's get going. Okay, we're going to be talking about radicals this whole video, and that's going to be any number written using this symbol, which we call a radical sign. It's also, it's a square root symbol, right? So when we take the square root of a number, we write it like that, okay? And that's going to be interpreted to be the positive square root if I don't write anything else. So what I mean by that is when it's square root of 9, that's 3, all right? Yes, it is true that negative 3 squared is also equal to 9. There are going to be times when we'll use a plus or minus, and I'll discuss that in just a few minutes. So for right now, just anytime we see a square root of any number, whatever it is, it's going to be interpreted to be positive, all right? Sometimes we call that the principal square root. Moving down below, a radical is going to be real, or a square root at least, is going to be real only if the number underneath the radical is bigger than or equal to 0, because we can't take the square root of a negative number. We talked about that back in chapter 2. So if I had the square root of negative 9, that's not possible. I can't multiply two real numbers together that are the same number and get negative 9. That would end up being an imaginary number. And this entire course is all about real numbers. We're not going to be discussing imaginaries. We can also deal with like cubed roots. Most of our course is going to really just deal with square roots, but there are cubed roots and other higher roots. We use this notation here. So a cubed root's got a little tiny 3 kind of sitting in the radical there. And that just means that we're taking a number, multiplying it by itself 3 times to get that value right there. So like the cubed root of 8, that's equal to 2, because 2 times 2 times 2 is 8. The cubed root of 27 is 3, and so on. Cubed roots, the number underneath can be negative because the cubed root of, say, negative 8 is just negative 2. Negative times a negative times a negative, that could be negative underneath, so there's no problems there. But like I said, most of our course is going to deal with just square roots. I'll show some cube roots examples to show you how to extend some of the ideas from this video, but for the most part, we won't worry about them too much. And this also is reviewing from chapter 2. A number is going to be irrational if we cannot write it as a quotient of integers. Now, radicals could be rational. For example, right down here, the square root of 4 is 2. That's 2 over 1, clearly rational. Square root of 9 over 16, that's the same thing as the square root of 9 divided by the square root of 16, which is just 3 over 4. That's rational. But not all radicals are rational. If a radical is irrational, it gets a special name. It's called a surd. And that might be a new word to you. 2 examples of surds we have down here at the bottom. Again, that's just a square root that doesn't have a perfect square under it. 2 more examples of a rational radical might be the 4th root of 16, because the 4th root of 16 is 2. And a surd might be the 4th root of, say, 15, because there's no perfect 4th of 15.
Legend has it that the man who first proved that the square root of 2 was an irrational number was rewarded for this by being thrown off of a boat and drowned to death. The ancient Greeks were crazy people, man.
Simplifying radicals, hopefully not a big deal. Basically, if we got 2 numbers that are being multiplied underneath the radical, we can split that up as 2 separate radicals that are being multiplied, and same thing with division. Depending on the problem, it might be easier for you to have 2 radicals, or it might be easier for you to consider it as 1. You have to figure it out as you go. Let's just look really quickly at some simple simplification. First of all, shortcut city right here. Anytime that I see a square root of something and then it's being squared, I know that those two are going to cancel each other out. So the square root of 5 squared is just going to be 5. There's no need to show any work. The long version of that, maybe I would write that as the square root of 25, since 5 squared is 25, and then I know the square root of that. Okay, same thing over here. It's a thing that's being squared, and I see that the inside's got a square root, so it's just 1 over 5. Of course, the square of 1 is 1. Some other quick ones here. We've got the 2 times the square root of 5 all cubed. Okay, so when we do that, we can write it out 3 times. And then whatever, the book has them rearranged here. That's cool. We know that 2 times 2 times 2 is 8. I know that these two together make 5. And then the last one's just left over. And 8 times 5 is 40. We got a similar thing happening on the right. It's always a good idea to collect your non-radical terms and deal with them separately. So we've got negative 2 multiplied by 3, which is of course negative 6. And then you deal with your radicals. We got square root of 5 times square root of 5. Again, that just gives us 5. 6 times 5 is 30. Make it negative. Boom, we're done. Here's 2 more. You can pause the video now if you want to look these over and think about them. And here's just a few with division. Again, on the left, 32 divided by 2 is 16. And I know the square root of 16 is 4, so that's easy. On the right, let's ignore this 2 in the denominator for just a second, and notice that the other two numbers are 12 over 3. So if we consider that as just the square root of 4, that becomes an easy problem as well, and we just got half of 2, which is 1. All right, section B. So we're going to try to simplify radicals now. And the way to do that is we're going to find the biggest perfect square, as long as we're doing square roots, of course. We'll find the biggest perfect square that goes into the number. So with 28, this is pretty easy. 28 is just the same as 4 times 7. And then we can break it up into two radicals, mentally, preferably. I don't want you to have to write this step down. And then the square root of 4 is just 2. So we've got 2 root 7. At first, maybe you want to write down this first step, but then from there, hopefully you recognize the square root of 4 is 2, and you've got your answer. Okay, some problems might be written in this form. So the math here is easy, but the question might confuse you if you've never seen it like this. So we're being asked to write it in simplest form, and they want our answer to look like this: a plus b times the square root of n. We are told then that a and b are rational numbers, and that n is an integer. So we're going to keep simplifying our answer until it looks like this form. Okay, so one way to do this is, since we've got a difference in the numerator, we can break up that fraction into two separate fractions, right? So we've just got 9 over 6 minus the square root of 75 over 6. But 75, we can simplify that to 25 times 3. And 25 is a perfect square. And the square root of 25 is just 5. So 9 over 6 simplifies to 3 over 2. That's our a value. And then the square root of 25 we said was 5, so we have 5 over 6 times the square root of 3. Negative 5 over 6 will be our b value, and 3 would be the value of n. And we see that our a and b are rational, and or our n is indeed an integer. Okay, we're on to section C now. So we can add and subtract radicals really easily. We just think about them as though they're like terms. So if we've got the exact same radical, like we have down here, it's as easy as saying 3 minus 4 is negative 1. So we have negative 1 square root of 2. Over here on the right, I notice these two are like terms, and these two are like terms because they have the same radical attached to them. 5 minus 3 is going to be 4 square roots of 3, and 2 plus 7 is 9 square roots of 5. Here's another example with fractions. Remember that when we add and subtract fractions, we need to have a common denominator. Other than that, nothing fancy here. Section D is about multiplying. So we need to remember all the stuff we had from chapter 3 with expansion. We definitely want to be on the lookout for our shortcuts from back in chapter 3. So a plus b squared, a minus b squared, or a plus b times a minus b. But in general, we're just going to use the distributive property. So here's 4 examples, and I'll just talk about, let's see, I'll choose this one in the lower right because it's probably the most complicated one. So we distribute negative square root of 3 times 7. That'll be right there. And then we'll do negative square root of 3 times negative 2 times the square root of 3. Now there's nothing to do for the negative square root of 3 times 7. That's just going to be left as is. And then for the other two, I notice that I have a square root of 3 times the square root of 3, which is going to be 3. So we have negative 3 times negative 2, which is positive 6. Sometimes in doing this, you might have some like radicals that you get to collect. We'll see that more often when we have two binomials, say, multiplied together. This is just the same as when we had variables, though. We'll do 3 times 4, which is 12. We'll do 3 times 2 root 2, which is going to give us 6 root 2. We can do negative root 2 times 4. And then we can do negative root 2 times 2 root 2. Again, we have a root 2 and a root 2, so they make 2. And 2 times 2 is 4. And then when you combine all the like terms here, I notice that I have constants, 12 minus 4, which is 8. And then 6 root 2 minus 4 root 2 is going to be 2 root 2. We can square binomials. Here we're using the shortcuts in these methods. Remember that if you don't feel comfortable with those, you've got to rewrite these out in long form so that you don't skip any of the multiplications. But otherwise, I think these two are pretty straightforward. Both of these examples are making use of the other shortcut of a plus b times a minus b equals a squared minus b squared. So we don't need to show all the steps because things are going to cancel out. Over here on the right, we've got our a value is 2 root 3 and our b value is 5. So 2 root 3 squared minus 5 squared. 2 root 3 squared, 2 squared is 4, root 3 squared is 3. 5 squared is 25, so we've just got 12 minus 25, which is negative 13. And we're in the last section now, so this has to do with something called rationalizing the denominator. Anyway, if you have a radical in the denominator and you wanted to get rid of it, the way you would do that is you're just going to multiply your fraction by a fancy looking 1, and that 1 is going to be made up of your original denominator divided by itself. So we see that right here in the first one. We're multiplying here by 1. It's just root 3 over root 3. Clearly that's equal to 1, so we're just changing the way that the problem looks. In the middle one, our denominator was root 5, so we multiply by root 5 over root 5. And in the third one, our denominator was 2 times the square root of 2. We could have multiplied by 2 root 2 over 2 root 2, but that's actually just extra work. We'd end up simplifying afterwards, so it's fastest just to use the radical. And we see that when we do the multiplication now in all three of these, the radicals in the denominator end up canceling out, giving us a denominator that is rational, hence the name rationalizing the denominator. I know I said we weren't going to focus on cube roots, but I want you to think about this. What if I wanted to rationalize this denominator? It would not work to just multiply by the cubed root of 2 over the cubed root of 2 because those two in the denominators aren't going to cancel each other out. I'm just going to end up with the cubed root of 2 squared, which is the same as the cubed root of 4. And that doesn't simplify to anything. That's still irrational. So how could we address this? Well, if we take the cubed root of 3 squared, now all of a sudden, my denominator becomes the cubed root of 2 cubed, and now the cubed root and the cube are going to cancel each other out. And that'll give us just 2 in the denominator, and then my numerator would be 3 times the cubed root of 2 squared, or we could call that 3 times the cubed root of 4, all divided by 2. If I had the 4th root of 2 in the denominator, then I'd need to multiply by the 4th root of 2 cubed, because then these two together would give me the 4th root of 2 to the 4th. See the pattern here? Here's a little more complicated one. Here I've got the 7th root of 2 but I've already got it squared. So what do we need to multiply here? The 7th root of 2 to the 5th, because now when I multiply, I'll get the 7th root of 2 to the power of 7. If you're looking for like a generalized formula for this, you can look down below. Obviously, the 3 and the 2 are just two arbitrary numbers. They could really be anything. But whatever type of root we're taking and whatever exponent it's raised to, we need to multiply by the same type of root, of course, and then raise to the power of that root minus whatever that other number was. Because when we use the property of exponents, when we multiply these two together, the new exponent we get is going to be the sum of m plus n minus m. And the m and the negative m will cancel, and that'll just give us n. And so we'll have the nth root of something raised to the power of n, and they'll cancel out, and we'll be good to go. But like I said, we're dealing with square roots in this course. This is all just bonus math. Things get a little more complicated if our denominator has a binomial in it. So we'll be looking at problems that have a real part, or excuse me, a rational part like a, plus an irrational part of the form b times the square root of c. And the trick to this one is to use something called the radical conjugate. Conjugate is just a fancy word. It means we're going to change the sign of one of the terms. If we originally had a plus b times the square root of c, we're now going to use a minus b times the square root of c. If we originally had a minus, we're now going to use a plus. This looks more complicated than I think it is. Let's see an example. So my denominator here is 3 plus 5 times the square root of 2. So in order to rationalize this denominator, we're going to multiply here by 3 minus 5 times the square root of 2 over itself, because that's just a fancy looking 1. And then we're just going to practice the skills that we saw earlier. The numerator is easy because it's going to be 1 times all that stuff. So that's what we got there. And then the denominator, again, check this out. Shortcut, because it's 3 plus 5 root 2 and 3 minus 5 root 2. 3 times 3, that'll be 3 squared. 5 root 2 squared. 3 squared is 9. 5 squared is 25. Root 2 squared is 2. 25 and 2 makes 50. And then we're just simplifying from there. Here's another more complicated example, but it's got all the same stuff we've been talking about. So we've got two numbers that we're trying to subtract, but they're both fractions, so we need to have a common denominator. That common denominator is just 1 minus root 3 times 1 plus root 3. Look, I know there's a lot here. What I really recommend you do, if you're watching this at home, is try to work this out yourself. Don't just stare at it on the screen, because oftentimes when we see work already written down, it makes perfect sense, but we would still struggle to come up with it ourselves. Trust me, every math teacher in the world has had an uncountable number of students say, hey, it makes sense when you do it in class, but I can't figure out how to do it on the exam. And that's because it's just easier when we see someone else doing it. It's also kind of like when you hear a song on the radio or whatever. You can sing along to it perfectly and know every word, but if you were asked to try to sing the song just by yourself without any backing track to help you out, all of a sudden it's much harder to remember those words that you knew so well just a few moments ago. So please take a minute, try to work this one out, because it's the most complicated thing we'll see in the entire chapter. And if you got this correct, then you're good to go.